Okay, so good morning, everybody. I hope you had a nice weekend. Now we are back on stage, and we have the pleasure to have Serena Viti this morning, starting the session. Serena is from Leiden and Bonn, and she will talk about the extragalactic astrochemistry and from nearby to high redshift galaxies. So the stage is yours.
Thank you, Emmanuel. Hope you can all hear me. I think you can. Thank you for being here so early at 8:30. So this lecture, I hope, will be an overview of the topic of astrochemistry, but targeted or concentrated on extragalactic environments. Please feel free to ask me questions during the lecture, and it can be quite modular in the sense that some of you will know quite a lot about what I'm talking about, but some of you will not. So I will just adjust as I go along. So first of all, let me start for those of you who do not work in sub-millimeter astronomy, or in other words, you don't work with molecules. Let me just highlight why you should care about molecules if you care about understanding galaxies, galaxy formation and galaxy evolution. So let me start from the basics. Why are molecules important in astronomy? And you will see, I hope by the end of this lecture, that molecules can be excellent tools if you're interested in the physics and in the history of galaxies. So first of all, the reason why molecules are important is because they're essentially everywhere where you have temperatures of less than a few thousand Kelvin and gas densities which are greater than about 10 hydrogen atoms per centimeter cube. So in environments such as that, molecules will be present. In fact, if a gas is about less or equal to 100, 200 Kelvin and has a density higher than about 1,000 per centimeter cube, then the gas will be almost entirely molecular. And so, as you shall see later, these are the environments where stars forms, for example. So you already know that where stars forms, molecules are going to be one of the main players. Although these regions are relatively small in terms of volume, they are compact, they tend to be where most of the activities in galaxies occur. So basically, if you're not looking at quiescent gas, often you're looking at gas where molecules are present. Okay, let's first set the scenes. What are these regions where I say molecules are present? So this is a very basic list. It's a list of regions which, as I wrote there, this classification is done really with our galaxy in mind, but I do think that it's still valid for extragalactic environments. So we are not going to really concentrate on most of these regions, of course, but have a look here in the middle, right? So here is where molecular clouds, cores that have not formed stars but will be forming stars are, and eventually disks where planets are, okay? I know you may be thinking, but you are in theory going to talk about extragalactic environments. So why are we talking about clouds and stars? Because at the end, what I want to convince you is that the same processes that occur in our own galaxies are occurring in other galaxies too. And that now we have the sensitivities with telescopes to actually zoom in other environments, especially nearby galaxies, and actually resolve regions where stars are forming, okay? So these are the type of regions that we're going to look at. And I want you to just keep in mind order of magnitudes, the type of densities and temperatures that we'll be dealing with, okay? So this is what we would call dense, 10 to the 5, 10 to the 6 per centimeter cube, and relatively cool, so between 10 and 300 Kelvin. Those are the main regions that we're going to concentrate on. Okay, so what do I mean by molecular emission? What do I mean by molecules? Again, most of you will be familiar with that, but just in case you're not, what we observe when we observe molecular gas is something like that. So this is a counterplot of carbon monoxide. CO is the second most abundant molecule in the universe after molecular hydrogen, and hence we use it to measure the molecular gas of a galaxy. So why do we use CO and not H2? As we'll see later, there is a spectroscopic reason why we cannot really observe H2, molecular hydrogen, despite being the most abundant molecule in the universe. So as you can see from here, CO is very extended, okay? Even if you don't know anything about molecular emission, all these blobs here show that CO is everywhere. It's not homogeneous, it's in blobs, again, as you can see. And so we use it a lot as a proxy for molecular hydrogen, and hence as a proxy to measure the mass of a galaxy. So if all you're interested in is measuring the mass of a galaxy, you could probably stop here with this lecture, because that's all you need to know. You can observe CO and you can get more or less the mass of a galaxy. But of course, that's not all we're interested in. We want to understand the processes that go on in a galaxy. And so let's see how we can relate molecules to what's going on in a galaxy. So why is dense gas, where molecules are present, important? I'm going to give you 3 reasons. They are relatively vague and relatively general, but I think it's important really to set the scene and to motivate you to listen to an hour and a half of astrochemistry. So why is dense gas important? Well, I think I've already hinted at that. Dense cool gas is the reservoir for stars. So you need this gas in order to form stars and in order to form, of course, planets. So the way it happens is that you start from a diffuse cloud, of course, then you collapse, the gas becomes more dense, and at the end of that collapse, the star will be born, it will irradiate the environment around it, expanding the gas and returning to a diffuse state. So this is what I call the multi-million-year cycle, and that's not the topic of a lecture today, but of course, molecules here are very important tools to understand this process. But again, even if you don't care about star formation, you should care about dense gas, because it actually helps us to understand galaxy evolution. Okay, so again, you need to measure the molecular gas and then compare with the existing stellar mass, and this will give you some indication of evolutionary stage of a galaxy. Yes. I knew that. Yes, no problem. It's too high because I told cloud. So. Okay, no problem. Can you hear me still? Yes. Okay. So, all right. So that's why you should care about dense gas, even if you do not care about star formation. And then a third reason, again, for those of you who work with active galactic nuclei, dense gas, we actually now understood that it could be an excellent tool to understand AGN feedback. So for those of you who don't know what AGN feedback is, so every galaxy has a galactic nucleus. Some galaxies have an active galactic nucleus, and what that means is that it's a powerful source, a powerful energetic source, and produces outflows, which will contribute to feedback of material into the surrounding. And of course, surrounding AGN, you will have a lot of dense gas. So even if you don't see the AGN itself because it's obscured, you can observe the dense gas around it. Okay, so this is really helping us with nearby galaxies to understand feedback mechanisms. So these 3 vague reasons really set the scenes, and to understand many processes in modern astronomy involve cold and dense gas. And in particular, they involve the interaction of radiation, whether it's coming from a star or from an AGN, with the cold dense gas. And it's this interaction that really helps us to understand what's going on in a galaxy. You want me to try again? All right, is that better? Yes, okay, all right. Cool, okay, right, so I've told you why molecules are important and where they come from, the dense gas. How do we observe molecules? We observe them mainly in the sub-millimeter and infrared part of the spectra. So here, I always have to show this, and I probably will show it one more time during this lecture. This mess here is the spectrum of the nucleus of one of the nearest galaxy, NGC 253. This is a starburst galaxy, so there is a lot of star formation going on. This is a spectrum taken by ALMA, the interferometer, and all this here are real molecular lines. You can't read the labels, and that's almost deliberate because there's so much, so many lines. It took many, many months to identify them all, okay? And each line has a story to tell. So you could spend decades just analyzing this little piece of spectrum and derive information about the different places in the galaxy. So this is a sub-millimeter spectrum for you. And then in the infrared, of course, now we got the JWST, but before that we had Herschel. And also in the infrared, you can observe a lot of molecules. This is Sagittarius B2, so it's towards the galactic center. These are lots of molecular lines, both in absorption and in emission. And the infrared part tends to trace warmer, hotter gas, and the sub-millimeter part of the spectrum traces the colder gas. So the combination of these two parts of the electromagnetic spectrum give us an overview of all the gas that can be traced by molecules. Okay, before we continue to talk about molecules, let me give an extremely short introduction of the ingredients that the dense gas has, because they're important. Of course, most of it is gas, and I don't think I need to say much about it. Just keep in mind that we have various elements, all fairly simple elements, but most of it is hydrogen, okay? Followed by helium, oxygen, carbon, and nitrogen. So those are the main ingredients. So most of the molecules will be formed by this type of atoms. And the other key point I want to make here, and I should say, my slides are many, I've sent them yesterday, and they're packed with text, but don't worry about it. That's mainly for reference to you. I don't plan to go through line by line everything, but I think the key point here is that the metallicity, or in other words, the amount of this material differs from galaxy to galaxy, okay? And that's important because that means that the molecular content can change from galaxy to galaxies. So that's the main thing I wanted to say about the gas. And then there is the dust, okay? Dust is very little compared to the gas, okay? The dust to gas ratio is 1 to 100 in our own galaxy. And of course, this can vary from galaxy to galaxy, but nevertheless, it's not as much as the gas. And yet, it's extremely important, as we shall see. And the main reason for us astrochemists that dust is important is because molecules form on top of the dust, and we shall see that later. So keep that in, keep this little picture here in mind. Okay, dust grains are excellent catalysts for molecular formation. And this is why, okay? So I said to you, keep this image in mind. I had forgotten that it was just the next slide. So the core of the gas is made up of carbonaceous materials or silicates, okay? And this is where a lot of the metals, so what we astronomers called metals, will be incorporated. So when the dust is formed during stellar evolution, it's made up of these metals here. But what happens is that as you are forming the dense gas and as the temperature cools, again, imagine the star formation process, atoms and molecules from the gas will freeze or will be deposited on top of the dust. And this dust then acts as a catalyst, which means that atoms can meet other atoms and I'm simplifying here, of course, but can meet other atoms and form molecules that otherwise would have not formed in the gas because they're too far apart. Okay, so that's why we call dust a catalyst, which I've been told by chemists that that's not the right word, but for our purpose, the dust is a catalyst. Okay, so a lot of molecules form on top of this dust and they form what we call the icy mantles. So that is important, as we shall see in a minute. Okay, so I told you where you can find molecules in space. I told you that they're important for major astronomical questions such as galaxy evolution, AGN feedback, and star formation. But let's zoom in a little bit on the actual role that these molecules have. Okay, I've hinted already, and please do stop me and ask me questions if I'm going too fast or if something is not clear. But now I'm going to give you three physical reasons of why molecules are important and what their roles is. So because you find them in dense gas, they trace such gas. Okay, this is gas that you cannot see it in the optical. So you need molecules to trace it. So anytime you're interested in gas which has these characteristics, as I already mentioned, you need to use molecules to trace it. Okay, so first reason why you would care about molecules is because they trace this gas. But the second reason is because actually they are the main coolant in us. So let me explain this a little bit. So molecules radiate at long wavelengths, so in the millimeter, as I mentioned already. And so what happens is that by radiating away the energy, they cool the gas. And it's this cooling that usually allows the gas to form stars. Because if you imagine during the collapse, you are collapsing the gas, and because of physics, pressure will start increasing and temperature would increase as you are collapsing the gas. So if temperature increases, then what you have is that the gas wants to return to equilibrium. And so hydrostatic equilibrium will be restored very quickly and stars would not form. So remember that clouds want to be in equilibrium, right? So to make them collapse and form a star, you need something that keeps that gas cool, and that something is molecules. So on average, molecules are needed to form stars. And the third one is because they control the level of ionization in a gas. And this is just a quick example here. These are two chemical reactions. One is with a molecule, an ion HCO+, and one is with magnesium, an atom. And this reaction here, okay, which essentially gets rid of the ion, is fast, and this reaction here is slow. And the reason why this is important is because you rely on these fast reactions to regulate the ionization of a gas. Why, again, do you care about the ionization of the gas? Okay, let's just take an example, the example of star formation. If you are in a gas which is highly ionized, that the ions which are tied to the magnetic fields, and I'm sure you should know all about it because you had the magnetic field lecture already, then many ion-neutral collisions will occur, and so also the neutrals will be tied to the magnetic fields. And so you have magnetic pressure. And this magnetic pressure would stop the gas to collapse. If the ionization is low, then the neutral gas is weakly bound to the magnetic fields because it won't have many collisions with the ions. And so you reduce the magnetic pressure and you allow the star to form, okay? So these are reasons why molecules are important or have a role for us. Okay, so now, again, I just put the slides back in just to remind you of the conditions that we're in. So if you stare at this for a few seconds, right, and you think about this condition here and you compare them with the condition in our own atmosphere, so in the atmospheres of planets, you realize that you are essentially in a vacuum, okay? I call this gas dense, but it's dense for astronomers, right? But if you think in Earth-like terms, this density is low. Equally, this temperature, I call it warm, 100 Kelvin, but if you think that our atmosphere is 300 Kelvin, this temperature is quite low. So in effect, you are in a vacuum, in a cold, ultra vacuum situation. So from your chemistry background, whether that's high school or at undergraduate level, you should realize that no chemistry really should occur, no molecular chemistry should occur in these conditions. So how come that we have molecules? The bottom line is that you wouldn't have molecules if nothing was happening in the interstellar medium, okay? Chemistry, interstellar chemistry, needs to be driven. Something needs to drive it. And we have four main drivers here. And everything that I talk about really is with in mind these drivers. What we use molecules for is not just to determine the conditions of our various objects, but to also understand what are the energetic processes going on in the galaxy. So in other words, what are the drivers? So I'm going to go quickly through some of these drivers. So we have starlight, so that's UV radiation, cosmic rays, dust, and gas dynamics. Down here, I have some pretty pictures to try for you to connect these drivers to real astronomical objects. So the starlight, of course, is the UV, so it comes from stars. So wherever you have star formation, you're going to have a strong UV. But in clouds where stars have not formed yet, so this is a very famous cloud, Barnard 68, it's dark, as you can see, the optical is dark, so it's a dark blob. So here, in principle, you should have no chemistry, and yet we see a lot of molecules, and this is because of cosmic rays, okay? The cosmic rays that are coming from everywhere, they drive the chemistry if you are in a very cold and quiescent gas. In this environment, you also have the dust. And as I mentioned earlier, because it's cold and because it's getting dense, it's a molecular cloud, atoms and molecules tend to fall on the dust. The dust acts as a catalyst, and so you can form molecules on the dust. And finally, we have gas dynamics. So what do I mean by gas dynamics? For gas dynamics, at least as far as this lecture is concerned, I'm mainly talking about shocks. So in environments where you have, for example, jets and outflow, like here, for example, this is a typical, it's called an Herbig-Haro object. Oh no, I can't remember. It's an object with a star somewhere here embedded in the middle. And as you can see, strong, powerful jets emanating from the star, from the embedded stars. And so you have this fast plasma hitting on a cold gas. And this will create shocks. And so this is a dynamical process which will drive the chemistry. Okay, so keep in mind, we have four drivers. Let's have one slide on this, but I think this will be covered mainly by Xavier's lecture. I think so. I'll only mention what it is with one slide. So if UV dominates, so if you have strong radiation, then you are in a situation where you're creating this small or large photon-dominated regions, or PDR for shorts. And this is a very, very simplified schematic. Sorry, I forgot to put the reference here. This is, I think, Hollenbach and Thielens, early 90s. And so what you have here, if you imagine just the gas as being a slab, you have ultraviolet radiation coming, impinging on a slab here, and essentially dominating the chemistry right into few visual extinction, so right into few optical depths, let's say. And so you are transforming the chemistry from ionized to neutral to molecular, depending on the strength of the radiation field. The radiation field is attenuated very quickly as a function of optical depth. So the dominated regions can be extended, but they tend to be very thin. So this is the slab part where the UV would drive the chemistry. And as I said, PDRs are probably going to be covered in later lectures, so I will not say anything anymore. That's the environment where the UV is a driver. Let me say a few more words about cosmic rays and the environment where cosmic rays drive the chemistry. Okay, it's a packed slide, but again, I just need you to concentrate on very few details here. The rest is for your reference. Cosmic rays literally start the chemistry because allow some ion-neutral reactions to occur very fast. And without, again, going into details, but please feel free to ask me if you're interested, what happens is that the cosmic rays collide with hydrogen, helium, and once is formed molecular hydrogen, and they give rise to these ions here. And these ions then can collide and can react quickly with all the other atoms, carbon, nitrogen, oxygen. Neutral reactions, so hydrogen plus carbon, is super slow, even if it's allowed to happen. While ion neutral, so H plus with carbon, is quick. That's why we need ions to kickstart the chemistry, and ions are formed via cosmic rays. That's why cosmic ray is a driver. Okay, so I already said this, but basically the bottom line of this is that ion molecule chemistry is rapid because it occurs on almost every collision, while neutral reactions are slow and can be forbidden when the temperature is low. So if you are in a dark cloud, neutral reactions are either very, very slow or it's not occurring at all. And so you need an ion to collide with a neutral. Okay, so cosmic rays kickstart the chemistry when it's dark. Okay, so again, another slide packed with text, but here the following, that although cosmic rays can kickstart the chemistry, of course, they can also destroy it, right? So chemistry is extremely nonlinear. And this is one of the reasons why the field of astrochemistry is here, because it's not so easy to interpret molecules. The type of reactions, therefore, and the type of molecules that cosmic rays can create is limited. Because, as I said, there is this balance between formation and destruction that create a limited networks of products. And yet, in the interstellar medium, we see very complex big molecules, like this one, for example, CH3COOH. So here we have four heavy atoms, 2 carbon and 2 oxygen. So how do these big molecules form? It's not through cosmic rays. Okay, so we need another driver for big molecules. And that other driver is dust. Okay, so again, I've already mentioned this, but it's so important that I will mention it again. A lot of the big reactions, a lot of the big molecules are formed on the top of this dust. That's why, for us astrochemists, dust is so important. So the process is quite complex. I will not go into details, but one of the main type of reactions that is very easy to occur on the dust is what we call hydrogenation. So that's when hydrogen combines with other species until saturation, okay? And so a lot of the water, ammonia, methane form on the dust. So you might say, okay, it's on the dust, why do we care, right? We care about the gas. Well, if you have any energetic process, whether that's a star forming or a powerful active galactic nucleus, that will irradiate this dust, warm it up, and lead to the evaporation, the sublimation of whatever molecules are formed here. This means, okay, that the gas before something happened, let's say a star, so in that dark blob that I showed you, and the gas after something happened, let's say a star is born, will look very different. So if you could take a snapshot of a dark cloud and then a snapshot of a star-forming region, let's say Orion, the two chemical signatures will be very different. And it's by using astrochemistry and bridging the knowledge between the pre-star and the post-star chemistry that you can build up a picture, a scenario of how that process occurred, because you can't observe a star in the forming. So you do need to use a proxy, and molecules are such proxy. And by the way, H2, which is the most common molecule and the reason why we're all here, why stars are here, et cetera, can only really form in the dust, on the dust. So even if you don't care about any molecule at all, but just H2, dust is essential because H2 in normal conditions cannot form in the gas. H plus H does not happen, all right? So you need the dust to act as a catalyst to even form H2. Okay, and the last driver, gas dynamics or shock chemistry. Again, this may be covered in other lectures, but let me just remind you what a shock is. A shock arises when you have an external event, a collision of two clouds, for example, or the expansion of an H2 regions, or again, an outflow or a jet. And this drives a perturbation that is faster than the local sound speed. Okay, so that's the shock. And in this case, the kinetic energy is converted to internal energy, internal thermal energy, and the shocked gas is compressed and it heats up. So density increases and temperature increases. And the way that happens is different depending on the different type of shocks. We tend to have, well, there are different types of shocks, but simplifying, we have what we call J shock or jump shock. That's because in this situation, the velocity is quite high, the temperature very quickly, almost in step function, increases, and then very quickly cool. C shocks happen in environment that the ions, there is a lot of, there is a magnetic fields, and there's a relatively strong magnetic field compared to this environment. This is this B here, that is basically measures the strength of a magnetic field. Again, you know all about it already, more than me from last week. And basically, let's just say that it slows down the increase of temperature. And so the cooling also is slowed down, okay? So these are two types of shocks from our point of view. So for an astrochemist, these shocks, the C-type shocks, so the slower ones, C stands for continuous, are the most important ones. Okay, I already mentioned this, so I can keep going. So why are the most important ones, the C-type shocks? Because they tend to be non-dissociative. This means that don't destroy too much the molecules. More importantly, they don't destroy H2, okay? So if you don't destroy molecular hydrogen, then you can continue to have chemistry. If you destroy molecular hydrogen, your chemistry is kind of dissipating away. So we care about non-dissociative shocks. And as I mentioned, shocks are a driver. And the reason for that is because they augment, they increase the probability of reactions that without shocks would not occur. These are the so-called neutral-neutral reactions, the one that I was saying that in a dark molecular cloud are not efficient. Okay, do you remember I said ion neutral, efficient, neutral-neutral, not efficient? That's because a neutral-neutral needs a lot of energy. There is a barrier there to the formation, so it needs a lot of energy to occur. This energy can be given by the high temperatures created in the shocks. And so a lot of these reactions that would not happen in a dark cloud happens in a shock. And so you can form a variety of molecules that usually cannot form in a gas phase. Two key points to remember, again, for us astrochemists, is that through high temperatures from shocks, can boost the chemistry. They form a lot of molecules, but of course, they can also destroy the molecules because high temperature breaks the bond, okay? So very, very time-dependent chemistry. So this is a plot showing the abundance of some species as a function of the passage of the shock, so as a function of depth into the shock. And I really just want you to see the fact that some lines are wiggly and they go down, and some lines are kind of quite steady, okay? This differentiates the molecules that are managing to survive the high temperature and those who are not, okay? And so already you can see, if you're studying shocked environment, you can pick the molecules that you wanna use to study, right? Because, for example, if you're interested in observing the shock at play, then water is a very good molecule because it does not get destroyed despite getting to temperatures above 3,400 Kelvin. Ammonia, on the other hand, which is this one here, as the temperature increases, this one here, this curve here is the temperature, increases and then decreases. So as the temperature varies, ammonia gets quickly destroyed, okay? So again, a flavor for how molecules can be used. You can pick and choose your molecule, but you need to understand how and why molecules form and get destroyed. Otherwise, you don't know which molecules to pick to trace a specific process. Okay. So the second point that I want you to remember if you are in a shocked environment is that, again, is the importance of molecules. While the temperature is increased by dynamics, right, is caused by the shock that is acting as a piston and compresses the gas and the temperature goes up, the cooling is determined by the molecules. So the reason why the gas cools, okay, is because of molecules, or mainly because of molecules. So far, I've told you about gas dynamics. So emphasis on the gas. So the dynamics of the gas can create molecules. But actually, shocks can also act on the dust. Remember that the dust is made up of silicates or carbonaceous material in the middle, and then has this coating, this icy mantle that coats the dust, formed of many different molecules that are formed during a previous stage, okay? When the shock arrives, can actually not just sublimate this coating, but can spatter the dust. So can impact on the dust, spatter it. And this is how you return the so-called metals, so silicates and carbonaceous material, back into the interstellar medium. So shocks are very important for the elements in the universe as well as the molecules. Okay, this is a good point for me to stop for a few minutes, also to give you a break. You can just take a few minutes to breathe, or you can ask me questions as you like. It's just that now I'm moving on to a second part, so this is just the ideal point to have a little break. Yes?
Thanks. I started thinking a lot about the cosmic rays. Is there any idea of how these reactions, I'm guessing these are protons that interact with the atoms, and then they produce secondary electrons.
Yes.
So these electrons could be reaccelerated, I guess. So is there any research on how these reactions contribute to the resistivity at these scales? Because there is a friction between these two.
The resistivity,
yes,
for
diffusion of
for diffusion.
Yeah.
Yes, there is. It depends on what type of cosmic rays you're dealing with. So the ones that we care about are low energy cosmic rays. MEVs, exactly, MEVs. So so then the diffusion of the electrons you're talking about, right? Or the secondary electrons, yes.
Yeah.
So then I would say that it's not well known at all, but there are, I believe that there are studies on it, but I know more about the studies on high energy cosmic rays and that low energy cosmic rays, I think. Yeah.
Thanks.
I have a question about, you said the H2 formation depends on dust, and since, you know, in tidal there is a cosmic evolution, if you want, how dust properties will change drastically from present to past universe. So
yeah,
what's the
yeah,
link with
absolutely.
H2 formation?
Yes, so indeed, so the formation of H2 indeed depends on the dust surface, mainly on the radius. So, for example, when we do our chemical models where we have H2 formation on dust, this gets scaled depending on the metallicity, depending on the size distribution of the dust. So your H2 will vary as well, the amount of H2 that you have. And indeed, that's something, it's a recipe that you need to include in all your models. If you think that again, if you're looking at high redshift, for example, where the dust is different, and there are a lot of studies on the dependence on H2 formation on the dust. Again, from our point of view, while this is important, it's unwaveringly less important because H2 is so abundant that for us, all it needs to do is kick the chemistry going for the rest, right? So even let's ignore helium for now, but even carbon, which is the second most abundant element, if you ignore helium, because helium is not very reactive for molecules, even carbon is about 10 to the -4 compared to hydrogen. So the details of the amount of H2 that you form are not as important for us because only a fraction of that H2 is important to form other molecules, but that's for us. But for those who study high redshift galaxies, the dependence of H2 formation on the dust is indeed very important. There are different recipes that you can put in your models to account for the different type of dust. Yeah. And also depends on the temperature, and the temperature varies. Yeah.
Thank you. Any other questions? Don't be shy. No, not for the moment. There will be other opportunities after.
Yep, I can continue, no problem. Okay, so far I have essentially give you, a very quick tour of an overview of the importance of molecules, how they form, what drives them, what can destroy them, and in general, their role. I'm now going to switch a little bit gear and talk about, as an observer or as an astronomer, what can you do with these molecules? In other words, if you don't care, as many astronomers don't, about the chemistry itself, what can you do with these molecules? And this is a very personal and simplified sketch of how I see people dealing with molecules. Okay, so again, very personal, and you're free to argue about my vision of this. So there are those who really don't want to know much about astrochemistry. They don't care. They just want to use it as a tool, and they just want to use it to determine the characteristics of a gas at large scale, like say, they want to understand the molecular mass. Then they go this way. They take their observations, say CO. They quickly determine how much CO there is, unwaveringly. They get a column density, which is essentially a measure of the amount of CO that you have, and that's it. And then they put a cross on astrochemistry. They say, that's all I care, right? There are those that, is interested a little bit more in the physics, and they still want to use it as a tool, of course, but they don't just want to know the amount of that material. they actually want to see whether they can use that molecule to derive the physical condition of your gas. So gas densities, for example, and gas temperature. And then to do that, you usually need to go a little bit further than just the simple calculations in LT of a column densities. So they tend to, try to understand how matter is transported. So they use a radiative transfer type of model to derive not just the column densities, but also the gas densities and the gas temperature. That's great. And that's okay. That's what most people do. But the conditions of the gas as you see it now are not telling you much about what happened to the gas. So if you want to put it in the context of star formation or in the context of galaxy evolution, you need to go a step further. And this is what I call the astrochemist view in a sense. So it's this methodology here. It's a little bit more complex and requires careful interpretation. And this is, for example, what we do in our group. We tend to cover it all. So basically, we take the observations. We try to derive information by coupling radiative transfer models with chemical models. Those of you who are doing hands-on projects know a little bit about the chemical model already. And we iterate until these observations are actually telling us not just the amount of gas, the density, and the temperature, but also the history and the processes, the energetic drivers that led to those molecules. And this is what astrochemistry is. It's a really interdisciplinary field that needs a lot of chemistry, first of all, because these chemical models that allow you to understand the observations rely on laboratory experiments to give us all the spectroscopic and physical information about the molecules, as well as theoretical calculations, because sometimes the lab experiments are very slow, so they need to be aided with calculations. And in recent years, we use a lot of inference processing, you've learned all about that last week, to help us interpret the results. So it's a very well-rounded interdisciplinary field. And of course, in my remaining time, I won't be able to cover it all, but I'm hoping to give you a flavor of how we use molecules to interpret molecular observations in galaxies. So let me continue more on the observational side. So I've already mentioned that most of the detections occurs in the millimeter and this is submillimeters. These emission or absorption lines, they tend to correspond almost always to pure rotational transitions. Again, try to recall some of the spectroscopy that you may have done as an undergraduate. And in some cases, there are raw vibrational lines or vibrational lines that can be also present, especially in the infrared. So I won't cover here, of course, any spectroscopy, although it helps to understand spectroscopy in order to interpret molecule. But there are two concepts that kind of you need to grasp in order to really understand molecular detections, molecular emission and absorption. These are the energy level of a transition, E, and the rotational quantum number, J. These two information is what these two quantities is what gives you an indication of the temperature and the density of the gas. Okay, so it's important to keep them in mind. The other thing that I would like you to keep in mind is that not every molecule can lead to a rotational transition and hence to emission. The molecule need to have a dipole moment. Okay, so again, I won't go through this. Ask me if you like later, or have a look at any spectroscopic textbook. But basically, if a molecule does not have a dipole moment, you really don't get a spectrum, a rotational spectrum. And the reason why I mention this is because this is the case for H2. That's why we don't observe H2. Okay, so H2 cannot really be observed in the millimeters, okay? So H2 can only be observed if an electronic transition occurs. And that needs a lot of energy that you don't have generally in interstellar medium, okay, in a cold gas. So H2, apart from the very high temperatures during a shock event, it's not usually observed in quiescent, dense, cold clouds, okay? Hence why we need to look at proxies of H2, such as CO. This is simplified. There are situations where H2 is observed, but we won't cover them here. Okay, so another key concept to keep in mind that I don't have the time to go through, but I'm just putting the slide here for you later to have a look at is the concept of critical density. And for now, all you need to know is that each transition of each molecule has a specific critical density. Okay, so a critical density is the density for which the net radiative decay from a high level or an upper level to a lower level equals the rate of collisional depopulation out of the upper level. A lot of jargon here for those of you who don't remember spectroscopy, but what the consequence here is that if you are in a gas which has density which are much higher than the critical density of a specific transition, then you normally de-excite the upper state in a collision, and so you don't have emission. If a density is much lower, if a gas density is much lower, then you don't have much in the upper levels, and so you don't have an emission either. This is when you have a transition, okay? So at densities of the gas near the critical density, you have a maximum chance of seeing an emission of a line. So that's all you need to remember. And this is important because it's why each transition of each molecule trace a particular type of gas, okay? So that's why each molecule has a story to tell, because they don't all emit in the same gas. Okay, they have different type of emission and different strengths depending on the gas densities as well as other things. So again, this is going into the realm of spectroscopy, which you don't want to go today, but it's for your reference why molecules are, or why transitions can be very important. Multiple transitions can be very important if you are tracing multiple gas components. And finally, one thing that, again, I will mention throughout the rest of the lecture is this, that it's important whether the gas is in local thermodynamical equilibrium, or LTE, or not. Because depending on whether you're in LTE or not, your method to interpret molecules must change. Okay, so again, I won't explain it here, but keep in mind the concept of LTE. And this is, again, a slide for your reference with the different jargon we use in submillimeter. You have lots of temperatures. We deal with temperatures. So we have excitation temperature, that is the temperature gives the observed ratios of two energy levels. So it tells you how much of a molecule is up here, how much is up there in the different transition. Then we have the brightness temperatures, which is a temperature at which a black body would have to give the intensities that you're observing. We have a kinetic temperature, so that's essentially the temperature of the gas, which ultimately is what you really want to know. But what we observe is not the kinetic temperature, it's the antenna temperature. So this is what we measure with the submillimeter radio telescope, the temperature of the antenna. And then we have a main beam temperature, TMB. Again, a lot of jargon. This is here just for your reference, in case you come across these different temperatures. They're related, of course, okay? And there are formulas, and I'll give you this information. I've given you a lot of information in additional PowerPoint, additional PDF that I just uploaded this morning on the Slack channel. And that's just additional material, which is essentially practical formula to go from an observation to a quantity, a physical quantity, okay? So that's more the practical part, which could be important for those of you doing my hands-on project. Okay, so lots of jargon, but ultimately what we want to know, as I mentioned already, is the column density of a species, the gas temperature, gas densities, and so on, okay? So again, if you look at this material here, you can derive this from molecular observations. So let's assume that we have the methods and we can derive all this information about galaxies. Let me now go finally to talk about galaxies then, okay? So now that we are acquainted with how to observe and how to derive information from a molecule, let's use it, okay? So how can we use it? Well, are now detected routinely in galaxies. They started in the 1970s, but actually until only, let's say until a few decades ago, very, very few detections were taken due to the sensitivities of our telescopes, mainly CO, mainly carbon monoxide. Now we can observe molecules further and further away at higher and higher redshifts. And I think, I'm not even sure I'm up to date here, but I think in 2023 is when we identified carbon monoxide at a very high redshift, so 7.5. I have a feeling that there is one at 8 now. I don't remember. But in any case, this is remarkable, really, because at these redshifts, we were at a point where the universe was just a few % of its present age. What this means is that molecules are very early on part of our history, okay? So they're really, really everywhere. So can we use these molecules to understand galaxies nearby and far away, as well as we can understand regions in our own galaxy, in the Milky Way? The answer is yes, but with caveats that remarkably, for those of us who come from a galactic background, only recently people are starting to realize and to take into consideration. And these are the caveats here. This is the first caveat, okay? In a galaxy, even for the nearest galaxies, the telescope beam will encompass a lot of gas components, okay? So in a beam, you're gonna have a collage of different densities and different temperatures. This means when you observe molecules, for the exact reason that I mentioned earlier, that different transitions peak at different physical conditions, when you observe molecules, it doesn't mean that they're coming from the same region, okay? So you have a blob there that you're observing, and then say that you observe carbon monoxide, silicon monoxide, SiO, and methanol, okay? Many astronomers, especially in the past, they take the ratios of these molecules and then they determine the densities, the temperature, etc. But these three molecules are very different and they will arise from different environment. CO is gonna probably trace tenuous gas. So the critical density of CO, especially of the low transitions, is low, which means the CO is gonna be everywhere. I show you that plot at the beginning, those contour blobs there of a galaxy, right? So CO, you can find it everywhere. And it's gonna trace maybe gas of 100,000 per centimeter cube. CIO, on the other hand, can only form if you release silicon from the core of grains. And if you remember from the first part of my lecture, the core of the grains, of the dust grains, can only be released if you have a shock that sputter this dust grain, and you release the Si. And then Si, silicon, will very quickly react to the oxygen in the gas and form SiO. But that means that SiO is not going to trace the same gas as CO. And equally, methanol, okay, methanol has a high critical density. So you will find it in star-forming region, but you're not going to find it extended in molecular clouds. So in general, external galaxies will contain a variety of regions and sources similar to the ones in the Milky Way, but all mashed up into your beam, okay, even for the nearest galaxies. So this is very important to consider. The second point to consider is that, of course, not every galaxy is like the Milky Way. Okay, we have lots of different galaxies, as we shall see in a minute. And these galaxies will differ not just in gas densities, but also in the strength of the interstellar radiation field, because some galaxies will have much more star formation than others. And so the UV radiation will be stronger. Cosmic ray rates. Cosmic rays, sources of cosmic rays are supernovae and galactic nuclei. So if you have a lot of stars, you have a lot of supernovae, and so your cosmic ray fluxes are higher, for example. And the dust property, as we mentioned before, when I got the questions about H2 forming on the dust. So what that means is that the amount of your H2 will be different, as well as your amount of carbon monoxide. But as I mentioned right at the beginning, many astronomers care about CO because they can use the so-called X factor, which is the relationship between the amount of H2 and the amount of CO, to determine the galaxy mass, i.e. the galaxy molecular mass, from CO. And this ratio is well known empirically from our own galaxy. But if we apply the same ratios for other galaxies, we might get the amount of H2 wrong. Okay, so this is why it's important to realize that. Let me skip this. Okay, so let's now have a little tour in the last 25 minutes or so. Let's have a little tour of the type of galaxies for which we observe a lot of molecules. We have starburst galaxies. These are essentially galaxies where a lot of star formation is occurring. And so you have episodic star formation, which means the gas changes with time a lot. And so the chemistry is very time dependent. You have a ULIRG, or ultra-luminous infrared galaxies, very beautiful galaxies. Here you have a lot of dust. And so you're going to have a lot of molecules formed in the dust, and a lot of molecules that will sublimate back to the gas. And these are really, really rich sources of chemistry. You have galaxies which we call AGN dominated. This means that their galactic nucleus is very active and source of cosmic rays as well as X-rays. As a consequence, the chemistry around these AGNs is very different from AGN-dominated galaxies compared to other galaxies. There are also galaxies, of course, that they cannot be defined as one or the other, right? So-called composite galaxies, for example, where you have a strong AGN in the middle, but you also have a lot of star formation going in the spirals. So that really complicates things, but they are the best astrochemical laboratories for us because we can study feedbacks and interactions between AGN and the starbursts as long as the galaxy is nearby. And one example of the galaxy is NGC 1068, some of you may know, is one of the most studied composite galaxies. As I mentioned, when you observe these galaxies, just keep in mind that you're observing a lot of gas into a beam. And this is just for you hand-waving a way of getting an idea of that, right? So basically, even for M82, which is a starburst, it's one of the closest, maybe the closest starburst that we have, the highest angular resolutions that you can reach with ALMA, okay, gives you 0.16 parsec. Now, for those of you who are extragalactic astronomers, you say, well, 0.16 parsec is nothing. But if you think in galactic terms, all right, 1/10 of a parsec is very large. You have a lot of different gas components there, right? If you think that our solar system, we are dealing with AUs, right? So 0.16 parsec can contain a lot of different gas components. Okay, so back to this beautiful spectrum here. We have all these components. How can we disentangle the different molecular components? Okay, so let's have a look. Let's start with normal galaxies, okay? Normal galaxies, spiral galaxies should be just like our own galaxy, the Milky Way. Actually, for these galaxies, there's remarkably little that has been observed, probably because they're too quiescent, although in recent years there have been quite few surveys that have given us a lot of observations. But most of the observations are of CO, okay? And I guess the message here is that when we analyze CO, we realize that it can vary by large amounts even within the same class of galaxies, okay? So in other words, the question to you is, can we really use our Milky Way as a proxy for all the spiral galaxies? And the answer really is no. We should really continue to observe normal boring galaxies if we want to understand star formation in the universe and not just in our own galaxy. In recent years, there have been observations of also other molecules. In particular, I want to emphasize HCN and HCO+, that for reasons that I cannot really go into, are two of the most observed molecules after CO in extragalactic environments. And this ratio, as we'll see later, is often used as a diagnostic of the type of drivers or energetic processes that go on in a galaxy. And in spiral galaxies, the spiral galaxies that have been surveyed, this ratio has been found to be higher than that in the Milky Way galaxy, which implies actually that the Milky Way galaxies must be one of the most boring galaxies, spiral galaxies that there is, because this ratio often is used as a diagnostic of strong energetics, okay? But still, in fact, much less, this ratio is much lower than found in starburst galaxies. And that makes sense because starburst galaxies are very energetic. Early type galaxies are another interesting type of galaxies because, of course, they're early type galaxies. So they can give us some information about how everything started in terms of galaxies. And until not long ago, it was believed that molecules were not present. And yet we now find many early type galaxies which have a substantial amount of molecular gas, okay? This means that stars may have formed much earlier than we thought. Observations of carbon monoxide in early type galaxies have revolutionized the way we think about star formation also in the early universe. And then we have starburst galaxies. Those are one of my favorite class of galaxies together with AGN. They're all sorts of shapes, as you can see. They're very energetic, which probably leads to all these different formation. And for the nearby ones, we can now zoom in and study the different processes. So again, I don't have much time left, but I just put a lot of information for the slides for you for later as a reference. So don't worry about reading it now. I think what I would like to underline here is the fact that I keep mentioning throughout the lecture. Different transitions trace different type of gas. Look at this, okay? So this is a starburst galaxy far away at Z equal 3.6, but it's strongly lensed, and as a consequence, the emission is enhanced, fortunately for us. And here we got a high J transition of carbon monoxide, a transition to water, and a transition to the ionic water H2O+, okay? And you don't need to be an astrochemist to realize that these are different blobs, okay, different morphologies. This means that if you can properly interpret each of these observations, you can determine the physical characteristics of different parts of this galaxy, okay? And I think considering the redshift, this is quite amazing. So on average, what type of characteristics can we determine for starburst galaxies? Starburst galaxies are some of the most studied galaxies, okay? Because we have some nearby. We're lucky. We have two, in fact, M82 and NGC253, which are super studied, okay? But in every single wavelength. And we can therefore take these two galaxies as an example for you and what I'm going to do in one slide is summarizing decades of studies on these two galaxies, okay? So this summary is by definition a simplification, okay? But by comparing and studying the molecular content in these two galaxies, we could already discover that NGC253 is younger than M82, okay? NGC253, the center, is dominated by shocks, by low velocity shocks, much more than M82. M82 is more dominated by PDR, so by UV. So remember the drivers, okay? I connect everything to the drivers. Here what I'm saying is that M82 on average is much more UV dominated than NGC253. Okay, NGC253 is dominated more by our dynamical drivers, shocks, and cosmic ray, while M82 is much more dominated by UV. Okay, and this is consistent with many observations. For example, the ions HOC+, CO+, H3O+, are much more abundant in M82, and this is consistent with the UV driver to be more dominant in M82, okay? So decades and decades of studies only summarized here in a very simplified way, but I think I wanted to show you is that how we can use molecules to determine the drivers, the physical processes which are dominant in a galaxy. AGN-dominated galaxies, same thing. What can we learn about that? Okay, so as I said, these galaxies are dominated by the fact that they have a strong active galactic nucleus, a lot of X-rays, a lot of cosmic rays. But as a consequence of this very energetic environment is that it's very hard to find unique molecular tracer that can disentangle the type of processes for us. So let me just take an example here. HARP-220 is one of the most famous, if not the most famous, ultraluminous infrared galaxy. A lot of studies on these galaxies, molecular studies, and what we discovered through molecular observations is that there are a lot of nuclei of activities, where there are at least 3 nuclei of activities here. The amount of HCN and HCO+ that we see means that there is a lot of high density gas in this galaxy, a lot. And for high densities, that means a large scale, more than 10 to the 5 per centimeter cube. That's a lot. As I said already, there are at least 3 nuclei, so 3 dense peaks, and this was obvious from a CO observation, so the 2-to-1 transitions. Actually, here is one of the few places where we see high vibrational states of a line, which implies, again, that there must be a very energetic driver, a driver that I didn't really mention, it's X-rays, but that's similar, chemically speaking, to cosmic rays, okay? And so these vibrational levels point us to an X-ray as the main driver, at least near the nuclei that we've detected with molecules. Okay, another interesting set of galaxies where you can study molecules is dwarf galaxies. I will not really say much about it, apart from the fact that interesting environment to try to measure gas that has H2, because yes, molecular gas, but not much CO. Okay, right at the beginning, I said to you that we can't observe H2, so we observe CO as the proxy for H2. Okay, but what if you have H2 and not CO? Okay, we didn't know that this was possible until a few years ago, but now we know that there is a lot of so-called CO dark gas. Okay, so this is basically gas where CO gets destroyed, but H2 doesn't. So it's a very specific type of gas. I don't have the time to go through it, but this is important because it means that if you're trying to determine the mass of, say, dwarf galaxies, you may be heavily underestimating it because you think that you can relate it to a CO. So you observe CO. CO is not very high in dwarf galaxies, and so you think that there is not much molecular gas. And that is not true. There have been examples where we've seen that there is a lot of molecular gas, but not CO. Okay, so keep in mind, if you're interested in dwarf galaxies, this is another use, another type of molecular observations that you need to be aware of. Okay, and another important topic that is only becoming really interesting from a molecular point of view in recent years is studying clusters of galaxies. One of the most important one is the Perseus cluster, and they're interesting because it's a cluster of galaxies, so you can imagine that the energetic processes are quite high. And again, in recent years, we've observed it in CO, and we also observed it in HCO+, CN, C2H. Again, I'm putting the slides here for your reference for later. I'm just giving you examples of how you can observe molecules pretty much everywhere, and if interpreted properly, determine what drives these galaxies, okay? In the clusters of galaxies, the main dominant process seems to be cosmic rays. Okay, whether this is because of cloud-cloud collisions or high rate of supernova, we are not sure. But cosmic rays seems to be driving the chemistry in clusters of galaxies. Okay, I will finish off. I've got to think about 10 minutes, 15. Okay, 15 minutes, so my last topic, but I think it's important for those of you who will if we ever observe molecules. Astronomers, extragalactic astronomers in particular, are very fond of molecular ratios rather than molecular observations in themselves. And the reason is because they remove a degeneracy for us, okay? So basically, because of the beam being so large, you don't know the geometry of the emission. And so people say, okay, if I observe ratios, so if I observe two molecules and I just use the ratio as a measure, then I can remove, I don't have to care about the size of the region because the molecules would come from the same region. I hope I'm now convinced that this is not the case, and as a consequence, molecular ratios can be used, but you have to be very careful to interpret them, because you might be observing a molecule that is coming from there and a molecule that is coming from there. And so taking the ratio means absolutely nothing because these two regions are unrelated, okay? Two of the most used ratios are HCN over CO, and that's because CO traces the molecular gas, but because its critical density is so low, doesn't necessarily traces the very dense molecular gas, i.e. where stars are forming. HCN, on the other hand, has a high critical density compared to CO, and so on average should be tracing the gas that may eventually form stars. So the HCN over CO ratio can give you the fraction of the gas that will be forming stars. So at large scale, this is a very pretty ratio to use. HCN over HCO plus is another very important ratio that I've already mentioned. And as we shall see in a moment, this is mainly used to trace the activity of active galactic nuclei. Okay, so it's often used to find AGN, the very obscured one, or to characterize AGNs, if you already know that there is an AGN there. Let's have a look at how we can do that. So, many observations have shown that this ratio is higher in the nuclei of galaxies than in either the starburst rings or in regions far away from the nucleus. So for example, in NGC 1068, which I mentioned already, being a composite galaxy with an AGN in the middle and the starburst rings around it, we find that this ratio is enhanced in the middle compared to the starburst part. Equally, in NGC 40389, this is the antenna galaxies, this ratio is higher in the nuclei of these two galaxies compared to the overlap region, so where the galaxies are overlapping, okay? So the conclusions from studies like this was that this is tracing AGNs because the high fluxes of cosmic rays and X-rays leads to an enhancement of the molecule HCN compared to the HCO+. So often this ratio is used as a proxy or as a tracer of AGN. This diagram gives you an example of it. Again, ignore the details, but just look at the blue and the red. The red and the blue seem to be very separated in this diagram. The red is the AGN, the blue is a starburst. It's showing you here that there is an enhancement of HCN compared to HCO+ that really seems to differentiate these two sets of galaxies. This diagram has become, from Izumi and collaborators, has become very famous. It's called the HCN diagram. However, the more you study something, the more outliers come to be. And some studies have found that this ratio is not always unique to AGN environment. So for example, here, this is a study by Arada and collaborators on a galaxy, I don't know, NGC 3256, I don't know the galaxy, but basically you can see from this blob here that it's mainly the same color, right? This blob is the HCN to HCO+ ratio, and it's more or less the same wherever you look, okay? It's not, this ratio does not seem to be stronger in the AGN, so in the nucleus. This result is kind of corroborated by a study, by a statistical study by Privon and collaborators that looked at a very large sample of galaxies, and they correlated the HCN over HCO+ to the luminosity of the AGN over the infrared luminosity. So this would be a ratio that gives you a ratio between AGN and star formation. And the bottom line is that a Spearman-Rank correlation coefficient gave no clear correlation. It doesn't necessarily mean that there is no correlation, but it means that it's not so obvious, okay? And this is corroborated by a theoretical study that was done as part of this, which again uses a radiative transfer model coupled with a chemical model. And to give you, and this is a lot of lines, let me just briefly explain it to you. So this is the ratio of HCN over HCO+ for different transitions as a function of time for different type of models where the cosmic ray flux varies, okay? And what you're seeing here is basically there is stochastic, okay, for approximation of a word in this sense. But basically what it means is that this ratio varies a lot by orders of magnitudes, okay? And so it's not so obvious that high ratio indicates an AGN. So it's clear that if you do want to use molecular ratios, you need to understand the chemistry behind each molecule, because the reason why this ratio varies so much is, I think, in the next slide. No, not yet. Okay. So the reason why this ratio varies so much is that each molecule has multiple paths of formation and destruction. So unless you understand how the molecules form, you cannot properly interpret the ratio. Okay, so let's see, for example, what causes the enhancement of HCN in this ratio, right? So people say this ratio is high towards AGN because the AGN have a lot of cosmic rays. Basically, what that comes down to it is the fact that the cosmic rays and the X-ray increase the temperature near an AGN, and these high temperatures allow some reactions. We have a high energy barrier, such as this one, CN plus H2, to form HCN. So this diagnostic is based on one reaction that can be enhanced at high temperature, but I hope that this already tells you why it cannot be such a unique ratio. You can reach high temperature in many different environments, not just where you have cosmic rays and X-rays. And so unless you exclude other environments, you cannot correlate directly the enhancement of HCN with the presence of an AGN, okay? This plot, which is very simplistic because it's very old, however, gives you a feeling. All you see is random dots. But what these random dots are this is the ratio of HCN over HCO+, again, for different J transitions as a function of different chemical models. forget what these different chemical models are, okay? But I can tell you, you can trust me when I say that all these models, 65 in total, so not many in our days, are all simple models where you vary various parameters, which are all reasonable parameters to vary. And yet, look at how much this ratio varies. This is in log space, okay? So very large ranges of values. So no wonder that you cannot map directly an enhancement in HCN with an HCN with an AGN, okay? Okay, so what can we do about it? Can we use HCN or HCO+ to trace AGN activity or not? So in this paper, very recent, and this is how I will conclude this, the Butterworth and collaborators have looked at many different galaxies and many different positions of galaxies at many different spatial resolutions. These different symbols here are the resolutions from 25 parsec to 20,000 parsec. And here is the HCN over HCO+ ratio. And again, I don't have time to go through this, but the bottom line is that the higher the spatial resolution, the more secure is this ratio as a tracer of AGN. In other words, yes, you can use HCN over HCO+ to trace AGN of activity over starburst activity, but only if you can observe a cloud scale resolution. Basically, when you go at lower resolution, gas components are mixed too much altogether in your beam, and this ratio becomes unreliable. Okay, so that's the first conclusion. When you're relying on ratios, know that this sounds obvious, or at least sounds obvious to me, but maybe it's not. When you rely on ratios, you need very high spatial resolution. If you're applying for ALMA time, and maybe this is the reason why you can use to observe high spatial resolution, okay? It's the only way to interpret molecular ratios properly, high resolution. The second one, okay? We are looking at really energetic processes here. Low J transitions are not really that good because low J transitions of any molecules tend to have a lower critical density. This means that we'll trace a larger range of densities, even low densities, okay? And so as a consequence, they cannot really give you a great tracer of an energetic process. You need high J transitions, okay? So these are the two conclusions for this. Different ratios can actually be used as great tracers, but you need to interpret it properly. You remember my sketch of going from observations to radiative transfer model to chemical model. This is what you need to do if you want to interpret molecular ratio. This is another one. SO and H3O+ is being used to determine the cosmic ray ionization rate in NGC253. This is one of the closest starburst galaxies. This is the disk of NGC253. These two molecules have been observed in lots of giant molecular clouds at giant molecular cloud scale. And models have shown that the ratio of these two molecules as a function of the cosmic ray ionization rate, no matter what the temperature of the gas is extremely well correlated, okay? At giant molecular cloud scales, not larger scales. So you can use these two molecules together if you wanna constrain the cosmic ray ionization rate of a galaxy, okay? Equally, HCN over HNC can be used to determine, again, this is NGC253, so same plots as before. If you observe HCN and HNC in the different giant molecular clouds, you can determine, so these are the different giant molecular clouds, you can determine the source of the energy, the dominant source of the energy in the different giant molecular clouds, whether that's in H2 regions, which means massive stars, or whether this is a supernova, okay? By looking at the ratio. Again, I cannot go into details of this, but again, this is done coupling radiative transfer model, chemical model, in this case, Bayesian inference as well, okay? So the interpretation of molecules is complex. So to sum up here, Ratios are great, but you do need to be careful when you interpret them. Time-dependent effect can be important. Different transitions can trace different parts of the gas. So you need to have information about the chemistry behind the molecule, the radiative transfer behind the J transition so you're looking at, and the time dependency of the chemistry, okay? So molecules have a very active role in controlling some of the most important processes in the universe at the low redshift and the high redshifts, but you need to use the right tool to interpret them. And so let me skip this, which is nice, but I don't have time. And let me put up some summary. So I hope I've convinced you that molecules play a key role in the formation and evolution of galaxies. Now we are in a wonderful era where we have both space and ground-based telescopes such as JWST, ALMA, and NOEMA that can give us high spatial and spectral resolution of both the sub-millimeter and the infrared part of the spectrum. And so we can really capitalize on the fact that, first of all, molecules are abundant everywhere. Every molecule has a story to tell, okay? Different molecules tell you different stories, and this is important in order to fully characterize a galaxy. But it's important to understand the basics of spectroscopy and chemistry to interpret these molecules. The important things to remember is that molecules are, chemistry is driven by different drivers, which is why you can use molecules to understand the different processes and the different drivers. There are challenges for extragalactic astrochemistry, and this needs to be kept in consideration. The unresolved beams, the unresolved observations that often we have, and the fact that each galaxies have all different physical conditions, and the only galaxy that we know very well is our own Milky Way. And often we should not be using the Milky Way blindly as a template. So that's it. There are many, many books. These are just 4 of them on these topics. Yeah, if you're interested, ask me questions, both now in the last 10 minutes or so and later on. Thank you.
Thank you. So now, yeah, the questions.
Thank you for the talk. So I have a question for the extragalactic part. You said like cosmic rays are usually 1 or 2 magnitudes higher than the Milky Way. Mm-hmm. So can they, I mean, is there any particular source, or is just with only the distant galaxies? And the second question is, can they also just destroy the molecules and hence we observe less chemistry in them?
So indeed, so there, in a sense, the fact that we are detecting high cosmic ionization rates is an observational bias, because if we want to study very well galaxies, as well as we study the Milky Way, we need to get the close ones and the bright ones. So both NGC 253 and M82, for example, they are starburst galaxies, and NGC 1068 is an AGN-dominated galaxies. So they're much less quiescent than the normal spiral galaxies that I mentioned, including the Milky Way. And so there is much more star formation that will create higher cosmic ionization rates. Supernova creates, produce cosmic rays. AGN produce cosmic rays. And so I guess we were not surprised when we measured higher, on average, cosmic ionization rates. We were quite surprised about how high they were in NGC 253, for example, and the fact that they were higher in NGC 253 in the nucleus than in NGC 1068, which has an AGN. So we were a bit surprised about that, but we were not surprised that they were high. And the second question, so I already forgotten.
Will they also like destroy this?
Yes. So I didn't have time to show it, and it was too much of a niche also, but there are a lot of studies, chemical studies, where we looked at the sensitivity of the chemistry as a function of the cosmic rays. And as you increase the cosmic ray flux, first you produce many more molecules, and then as you're increasing the cosmic rays, you start destroying them. The turning point seems to be about, so the standard cosmic ionization rate is about 10 to the minus 17, 10 to the minus 16 per second. When you get as high as 10 to the minus 12, you start destroying H2. And once you start destroying H2, the chemistry is gone, right? Yeah.
Thank you.
Any other question? Yes.
About the HCN molecule ratio in terms of HCN activity, does the nitrogen to oxygen ratio in ISMN, does it affect?
Yes, yes. So far, everything I've talked about was nearby galaxies where we think that the oxygen to nitrogen to carbon ratio is the same as in the Milky Way, okay, which is, well, is of course not set in stones. If you go to high redshifts, we expect the nitrogen amount to be quite different. If I remember some evolutionary models, which you know better than me, but they show different values for nitrogen at early times, right? So that, of course, will completely change it. So I will never, unless one does a study, trust the HCN over HCO plus ratio as a proxy for AGNs at high redshifts. On the other hand, we haven't yet observed these two molecules at high enough spatial resolution in galaxies where I would expect the nitrogen to carbon ratio to oxygen ratio to be very different. But when we do, then yes.
What about the HCN and HNC ratio you indicate?
Right, so that's very interesting. So in principle, that ratio could be more reliable at high redshift, in principle. However, there is already some debate in our own galaxy and in nearby galaxy that about what type of environment this ratio may be tracing. It's a bit complex in a sense, not complex, it's a bit long story, but basically we know the chemistry of HCN better than we know the chemistry of HNC. So if you look at databases of chemical reactions that we use in our chemical models, the HCN network is, I would say, quite complete, but the HNC network is much more limited. And whether this is a true limitation in the sense that, you know, there are only fewer reactions that form or destroy HNC, or whether we're actually missing some key reactions, I am not in a position to say. So I like that ratio, but I have some reservations when used because of that. The other thing to consider, and there are now been some really, really recent studies on this, is that we always not assume, but we have reactions that happens on the dust, but we include in our chemical models that forms HCN very efficiently. So that's basically CN plus H seems to favor the formation of HCN rather than the formation of HNC on the dust. But this is now being looked at from a theoretical computational chemistry point of view, and we're trying to see whether this is the same under every conditions or not, because that would also affect the HCN to HNC ratio. So it's complicated, but I would say that ratio should be more reliable in galaxies where the nitrogen to carbon or to oxygen ratio is different. Yeah.
Thank you for this very interesting overview. I have a small question about the chemical models and the redshift. So how is the redshift incorporated inside the chemical models? Is it biased to use the same ones that we use for the Milky Way for other sources?
Yeah, so that's a very good question. There is no direct parameter in our models that defines the redshift per se. So the things that we change are the dust to gas ratio, the metallicity, the sources of energy, and the different elemental abundances. And in some cases, depending on what type of model you're doing, you may change the cosmic microwave background temperature. But there's nothing else that defines the redshift for chemical models, apart from the elemental abundances, which of course are dependent, or we rely on stellar evolution models to tell us what they should be at the different redshifts.
Any other questions? I do have some.
Yeah.
So at some point you touched about the timescales, and I was wondering, in these models, when you're talking about very active galaxies, or what is the influence of the timescale of this event? Because having a cosmic ray ionization rate of 10 to the minus 12, I doubt it can be sustained during the entire life of a galaxy. So what's the final consequence of it?
Yeah. So indeed, indeed, in places such as starburst or AGN-dominated galaxies, one has to take into consideration the time dependencies. It's often something that is not done. I think in one of the plots, very quickly, I had shown models where this one, for example, where I was changing. So that's the time, and the cosmic rays is changing with time.
But it's a quite short time scale with respect to the lifetime of galaxies.
Absolutely.
So
but
how does it go back to normal after, or not?
Yeah. So
what is the imprint?
Yeah. So it's very hard to say for us, because you see, a chemical model, you can hardly ever go over, say, 10 million years, simply because depending on the condition, it either reaches chemical equilibrium or you are restarting the chemistry one way or another. And so we reset the time to zero, right? So I would say that in general, depending on your time scale, you may go back to, so you may have a cyclic picture where you have very diffuse gas, dense gas, then you have your processes, whether it's a star formation or AGN, then you have diffuse gas again, and you continue the cycle. But of course, the material will have, the initial conditions will have changed depending on how many generations of stars you've had. So that's all part of the initial conditions, which takes me to the fact that these days, because we know all those things, we cannot rely on a chemical model as a template. We need to run loads and lots of models changing the initial conditions a lot. And that's why we rely a lot on Bayesian inference and some machine learning techniques in order to really explore the parameter space. With all the caveats that you need to know some of the chemistry in order to be able to interpret this, black boxes of machine learning or inferences. So yeah, time dependence is extremely important. And it's not only important for that, it's also important because, and this is the part that I would have liked to show, but I couldn't, but I maybe can just put up to answer your question, this one. So this is time scales, hand waving with one equation, time scales that determine essentially the formation of stars, right? So you need all these time scales here, which is the free fall collapse, so gravity, cooling of the molecules that allow the gravity to happen, the chemistry that will change the ionization, et cetera, all these time scales, which there on the left and right side, I tell you what each time scales is important for, have to be more or less the same. Otherwise, star formation doesn't occur. And so when you start looking at high redshifts, right, and you start measuring these different time scales, so this is basically the time as a function of a different parameters, so cosmic rays, UV, etc., metallicity, and these are all the different time scales. It's only when they cross that you are going to have star formation, and they only cross at the conditions more or less of our Milky Way, spiral galaxies, etc. So when you have an extremely energetic galaxy, you may have bursts of massive star formation, but low mass star formation, which is, sorry, I should have specified, is what I'm talking about here, is an extreme function of all these parameters. So it's extremely interesting to see how chemistry really regulates the low mass star formation rates. And you could use things like that to determine whether in your galaxy you're going to have a lot of low mass and high mass compared to high mass. So basically they can influence the IMF, the initial mass function. So yes, time scales is very important to answer your question, yes.
Thank you. Any last minute question before the break? No. So let's thank Serena again. Thank you very much.